Imagine peering into the very fabric of our universe, zooming in past atoms, protons and quarks. Eventually, you would reach a point where our conventional understanding of space and time begins to break down. At this unfathomably small scale, something extraordinary happens. Space-time itself becomes a dynamic, frothy sea of constant fluctuations. This phenomenon is what physicists refer to as space-time foam or quantum foam, and it reveals the bizarre and unpredictable nature of reality at its most fundamental level. The concept of space-time foam was first proposed by physicist John Wheeler in 1955. Wheeler, known for his pioneering work in quantum mechanics and general relativity, envisioned the universe not as a serene, continuous backdrop, but as a stormy, restless fabric when observed at the tiniest scales. To understand this idea, we need to journey into the realm of the Planck scale, where distances are as small as 1.6 x 10^3 meters. Here, space-time is far from smooth. It is restless, agitated, and constantly changing, almost like the bubbles that form in a pot of boiling water. At the Planck scale, the known rules of physics start to disintegrate, giving way to the bizarre effects of quantum mechanics. The uncertainty principle, a cornerstone of quantum theory, dictates that energy fluctuations at such small scales are inevitable. These fluctuations, in turn, lead to the spontaneous creation and annihilation of virtual particle-antiparticle pairs. These ephemeral events cause space-time to warp and twist, giving it a chaotic, foam-like quality. This is where space-time ceases to be a calm and predictable fabric and instead becomes a bubbling, fluctuating quantum sea. To understand what Wheeler meant by quantum foam, it's helpful to think of space and time as something dynamic rather than static. At our everyday scale, space-time appears smooth, like the surface of a calm ocean when viewed from far away, with only gentle ripples and minor fluctuations. But just as an ocean hides turbulent currents beneath, space-time hides its restless, dynamic nature at smaller scales. In the case of space-time foam, we are zooming in to a scale where space and time are anything but calm. Instead, they are writhing with relentless activity. At this level, fleeting fluctuations in energy are so intense that they cause the very geometry of space-time to continuously shift. The constant interplay of energy creates tiny bubbles, warps and curves, as if space-time itself is foaming. Virtual particles pop into and out of existence, stretching and bending space-time before vanishing again, in accordance with quantum laws. The result is a picture of space-time that is anything but fixed. It's more like a frothing, ever-changing sea of possibilities. One of the most intriguing questions about quantum foam is whether it actually exists. Experimental evidence for quantum foam remains a challenging puzzle. Some experiments, like those observing the Casimir effect, provide indirect support. The Casimir effect, which measures the force between two uncharged metal plates in a vacuum, can be explained by the influence of virtual particles, hinting at the restless nature of space-time. These experiments suggest that the vacuum of space is not truly empty, but rather filled with transient activity. Physicists have also looked at gamma-ray photons arriving from distant cosmic events, trying to detect whether the predicted foaminess of space-time causes a slight variance in the speed of light as it travels over astronomical distances. Such variations could serve as evidence of space-time's quantum structure, but so far results have been inconclusive. The technology required to observe quantum foam directly is beyond our current capabilities, but the tantalizing prospect drives ongoing research and theoretical exploration. The idea of space-time foam has profound implications for our understanding of the universe. It suggests that at its most fundamental level, reality is in constant flux, a sharp contrast to the classical picture of a smooth and predictable cosmos that has dominated physics since Newton. Quantum foam represents a key aspect of the problem of reconciling quantum mechanics with general relativity, Einstein's theory that describes gravity and the curvature of spacetime. If spacetime is foamy at the smallest scales, then the unification of quantum mechanics and general relativity must involve understanding this turbulent fabric. This quest for a unified theory, often referred to as quantum gravity, remains one of the greatest challenges in modern physics. Approaches like string theory and loop quantum gravity are attempting to explain how these two pillars of physics can coexist, and the nature of spacetime foam plays an essential role in these pursuits. In summary, spacetime foam reveals a dynamic and unpredictable universe, challenging our understanding of reality and pushing the boundaries of what we think we know. It portrays spacetime as something dynamic, turbulent, and filled with possibilities, constantly influenced by the unpredictable dance of quantum fluctuations. Wheeler's vision of spacetime as a frothy, restless entity challenges our classical intuitions and suggests a universe where certainty gives way to probabilities, and the solid ground beneath our feet is anything but stable at the smallest scales. While we may not yet have direct evidence of spacetime foam, the concept captures our imagination and underscores the notion that, at the deepest level, the universe is filled with mystery and wonder. As technology advances and our theories evolve, we may one day be able to peer directly into this seething quantum fabric, unveiling the true nature of the cosmos and our place within it. To explore more about the mysterious and awe-inspiring universe, subscribe to our channel and join the conversation in the comments below.